Indeed logo. Text 1 search. All jobs. At Indeed ENG, monthly tech talks at Indeed's Austin headquarters, engineering.indeed.com. On the left, a presenter takes the stage in front of an audience. On the right, a slide deck. Text on slide, Indeed Engineering, engineering.indeed.com/talks, Twitter, @IndeedENG, go.indeed.com/IndeedENGtalk.
Thanks everyone for coming out here tonight. We're really excited to see a big group tonight.
Title, Tokens and Millicents, Technical Challenges in Launching Indeed Around the World.
So as Chris said, tonight we're talking about tokens and millicents, and really this is going to be a deeper technical dive into some of the issues that we faced in launching Indeed around the world. As Chris mentioned, this is the second talk in a two-part series about all of the challenges that we've had to address in internationalizing Indeed's products.
Text, Dan Heller, Engineering Director.
My name is Dan Heller. I'm an engineering director here at Indeed, and I focus on our products for employers.
We help people get jobs. A screenshot of Indeed search results for software jobs in Austin, Texas.
Here at Indeed, we're here to help people get jobs. And the major way that we do that is with our job search application. Here you can see a typical results page. Someone has come to Indeed to search for software jobs in Austin. And they're presented very simply with the jobs that are relevant to them. And that word's really important, simple. At Indeed, we think our product should be simple. And so the way that you get to this page is by just typing what you're looking for, software, and where you're looking for it, in Austin.
A screenshot of the search page with the term software in the what box and Austin in the where box. The Indeed logo is decorated with an American flag and a soccer ball as the dot in the lowercase letter I, text under logo, Go USA.
And also, as you can see here, we've got World Cup fever. So we're proudly supporting the US men's national team, and we're rooting for them as they play Germany tomorrow to get into the knockout rounds. Speaking of Germany, we also want to help job seekers in Germany. They also have World Cup fever.
Screenshots of Indeed search page with text in German, Japanese, and Greek.
And so we want to make sure that just like our products work great for job seekers in the US, we want to make sure they can help people find production assistant jobs in Munich, registered dietitian jobs in Osaka, and also assistant accountant jobs in Athens. And making sure that our products worked well for job seekers all around the world, we've had to solve a lot of technical challenges. Preetha's now going to talk about some of the challenges and improvements we needed to make in order to make sure our search results were high quality for job seekers around the world. And then I'll be back to talk about the improvements we made for employers.
Preetha Appan takes the stage. Text, Preetha Appan, software engineer.
Hi everyone, thank you all for coming. Really excited to see you all here. Thank you Chris, thank you Dan. I'm Preetha Appan, I'm a software engineer here at Indeed. I've worked on a couple of different teams like the job search backend and the resume backend, and now I'm working on recommendations. So you might have seen recent job searches on Indeed streaming here on the big screen behind me, showing what queries people are doing all around the world. Like Dan mentioned, we had to solve several significant technical challenges in order to make search work in languages other than English. And two terms that we use frequently when we talk about the quality of our search results are precision and recall. So I want to start by defining them.
A Venn diagram titled All Jobs. Two circles overlap, labeled relevant jobs and returned jobs.
If we consider the set of all jobs that Indeed knows about, then given a particular user's query, there's a set of jobs that's actually relevant to that query. And then there's a different set of jobs that a search engine actually returns. We want to maximize the intersection between these two sets.
Text, precision, positive predictive value. Number returned and relevant over number returned.
Precision and recall help you measure how well you're maximizing that intersection. So precision, which is also known as positive predicted value, is the fraction of return instances that are relevant. Let's really understand what precision means with an example here. So let's say we have a job seeker at Indeed who's looking for architect jobs, and we know that architect usually means building architect, not software architect. Now we returned 10 jobs, out of which 8 of them were building architect jobs and 2 of them were software architect jobs. That means that 8 jobs were relevant and 2 jobs were not relevant. So our precision would be 8 out of 10 or 80%.
Recall, specificity. Number returned and relevant over number relevant.
Recall, which is also known as specificity, is the fraction of relevant instances that are returned. Let's understand recall with a different example here. So let's say we have another job seeker who's looking for HR jobs, and we know that jobs that mention HR as well as jobs that mention human resources are both relevant to that job seeker. Now again, we have 10 jobs and all of them are relevant. 7 of them are, say, HR, and 3 of them say human resources. We return the first 7, but we fail to return the last 3 because they were not an exact keyword match. That means our recall would be 7 out of 10 or 70%.
Improving recall in job search.
At Indeed, we've built different systems to improve both precision and recall. In today's talk, I'm primarily going to be focusing on some challenges we had in improving recall in job search and particularly internationally. The first step in making any search work is to actually understand the content. For us, the content is just jobs. This is a job description in English.
Job description, English, Senior Software Engineer, Search, Indeed, Austin, Texas. Indeed.com is seeking a senior software engineer responsible for the information retrieval system that powers Indeed's job search website. If you are an engineer who is passionate about building innovative products.
It's for a senior software engineer in search. It's at this company called Indeed. You may have heard of it.
Preetha smiles.
It has all these sentences like Indeed.com is seeking a senior software engineer responsible for the information retrieval system, yada, yada, yada. So we want this job to show up in the search results if anybody searches for senior software engineer or information retrieval or Indeed. We want this job to show up. So in order to do that, we need to first take all these sentences and break them up into keywords or tokens.
Text tokenization. Orange boxes outline each word in the phrase Indeed.com is seeking a senior software engineer.
This process is known as tokenization. So that's illustrated here. So for this particular job, Indeed.com is a token, is a token, seeking is a token, and so on. Once we have all our tokens, typically when you're building a full-text search engine, you use an inverted index to actually make search work. If you're not familiar with inverted indexes, it's just like an index in the back of a book. So instead of words, we have our tokens, and instead of page numbers, we have document IDs. For us, the documents are just jobs.
Inverted index. A chart with 4 columns labeled Token, Job A, Job B, and Job C. Tokens include Assistant, Developer, Engineer, Lawyer, Paralegal, and Retrieval. Job A has checkmarks for the tokens Developer, Engineer, and Retrieval. Job B has checkmarks for the tokens Assistant, Lawyer, and Paralegal. Job C has checkmarks for the tokens Lawyer and Paralegal.
This is a visual representation of an inverted index with 3 jobs and a few job-related keywords. So you can see here that the keyword developer occurs in job A, the keyword engineer occurs in job A, the keyword retrieval occurs in job A. There are some terms that occur in more than one job, like lawyer and paralegal. You see them in both job B and job C. With an inverted index, we can very quickly find all documents that contain a particular token or a keyword. And we can also perform Boolean queries very efficiently, like give me all documents that contain both Java and developer. At Indeed, our search engine is built on top of Apache Lucene.
Apache Lucene logo. Text, open source inverted index implementation, fast, widely used.
This is a very well-known open source inverted index implementation. It's fast and widely used and well tested, so we use that here.
Tokenization with Lucene, Standard Analyzer, uses space and punctuation to determine token boundaries.
Lucene already provides a mechanism for taking free text and turning it into tokens. That's called analyzers. And there's this open source analyzer within Lucene called Standard Analyzer, which works by using space and punctuation to determine where tokens are. And however, we found that it didn't really work out of the box for jobs.
Standard Analyzer problems.
If somebody searched for C++ developer or C# developer and we used the Standard Analyzer, we would get C developer jobs. And that's not, they're going to be mad because that's exactly why they learned C++, right? So they don't have to write code in C anymore.
Preetha smiles.
The company O'Reilly would become two tokens, O and Reilly. So to fix these problems, we basically just forked Standard Analyzer.
Text, Job Analyzer, forked Standard Analyzer, modified it to make it work for jobs.
We call it Job Analyzer. We made a few simple modifications to make it work for the jobs domain. In early 2009, we launched the first set of non-English languages in Indeed. So we launched Indeed in French, German, and Spanish. This is a job description for a secretary in France.
A job description with French text.
The sentences still look pretty similar to English, so we didn't really have to make any changes. We were able to continue to use Job Analyzer and make it work in all of those languages.
Text, Chinese, Japanese, Korean, Cjk.
By early 2010, we started planning to launch Indeed in China, Japan, and Korea, which is known as Cjk for short, and I'll use the term Cjk throughout this presentation as an acronym for China, Japan, and Korea, or Chinese, Japanese, and Korea.
A job description with Chinese characters.
This is a job description in Chinese. This looks very different from any of the job descriptions that we had seen so far. Notice that it's basically just a stream of characters. There's maybe a couple of white space, there's a couple of punctuation here and there. There's no white space.
A job description with Japanese characters.
This is a job description in Japanese. The Japanese writing system actually has 3 different character sets, and I'll highlight them one by one.
Several characters highlight in orange.
The first writing system is Kanji. It looks similar to Chinese characters.
Several characters highlight in orange.
The second writing system is Hiragana, and the third one is Karakana. Hiragana and Karakana are used for some grammatical elements and some foreign words, but Japanese job descriptions contain all 3 different characters.
Text, Chinese using Job Analyzer. Gray boxes outline 3 groups of Chinese characters.
If we took the job analyzer that we had and attempted to tokenize Chinese, these are the tokens we would get. We would get 3 tokens because there's no white space and there's 2 punctuations, or 3, I guess. So these are the 3 tokens.
The first token highlights in orange.
That first token, which is 11 characters, is actually an entire sentence in Chinese. It means daily inspection of electrical equipment plant-wide. For this job to actually show up in a search result, a job seeker would have to type that exact 11-character sequence. So we all know that job seekers would tend to look for keywords like electrical or inspection or electrical equipment. Nobody's going to look for daily inspection of electrical equipment plant-wide. So this was a problem that we had to fix. Essentially, using a job analyzer in China, Japan, and Korea meant poor recall. Basically, you wouldn't be able to return any jobs.
Text, Cjk Analyzer, bigrams.
There's actually a naive way to solve this problem using bigrams. There's a different open source analyzer called Cjk Analyzer that takes this approach.
Japanese characters.
The way bigram tokenizers or bigram analyzers work is that they don't really know anything about that particular language or sentences or words in that language. They simply take adjacent characters and turn those into tokens. This is some Japanese string. I'm going to show you how it looks like with a bigram tokenizer.
The first 2 characters highlight in orange.
The first 2 characters means medical. Okay, that turns into a token.
The second and third characters highlight in orange.
The second and third is not really a word, but whatever, it becomes a token. The third and fourth characters means affairs, and that turns into a token. And so it keeps doing that and creates lots and lots of 2-character words that it adds to the inverted index.
Text, use Bigram Tokenizer on query.
This is somewhat reasonable because some of these languages have lots and lots of 2-character words, but there are some problems with this approach. Now, to actually use the Bigram Tokenizer at search time, what you would do is do the same thing to the query. So here's a Japanese query for Tokyo Prefecture. So with the Bigram Tokenizer, we take the first and second character and we turn it into a token.
Underneath the query for Tokyo Prefecture, 2 arrows point to 2 groups of 3 characters. On the left, the first 2 characters in the string highlight in orange. Text, Tokyo.
That's actually Tokyo. Then we take the second and the third character and turn that into a token, and that's Kyoto.
On the right, the second and third characters highlight in orange. Text, Kyoto.
So the string Tokyo Prefecture turned into Tokyo and Kyoto. Kyoto is actually a different city in Japan. This means that people searching for, say, Tokyo power plant jobs are going to get Kyoto power plant jobs, which is not what they wanted.
Bigram Tokenizer drawbacks. Poor precision, too many terms.
So essentially, with the Bigram Tokenizer, you can get good recall, but very poor precision. The other problem with Bigram Tokenizers is that it explodes the number of terms in your inverted index. If you had, say, a 100-character string with an average word size of 3, instead of getting 30 tokens, you'll get 99 tokens, and it's that much additional space to store your inverted index.
Properly tokenize Cjk.
So we knew that we needed to properly tokenize China, Japan, and Korean text in order to be successful.
Accent and gender normalization.
Around about the same time, we also started to run into accent and gender normalization issues. This is secretary or secrétaire in French. This is also the part of the presentation where I'm going to pre-apologize for butchering French and German words. But anyway, this is secrétaire or secretary in French, and it's spelled with an accent. That's the right way to spell it, but both job seekers and job descriptions use that form without the accent. Vendeur and vendeuse means salesperson male and salesperson female, but people searching for one or the other should get both kinds of jobs. That last example is really interesting, promoter with an @ symbol at the end. That's something that we see only in Spanish job descriptions on the web. Like, you wouldn't see it in printed material, for example. It's just a more recently evolved form for doing gender neutral notations. So what that's trying to say is that I want both promoter and promotera, which is the female form. We realized that if we had the language of the job, then we could make intelligent decisions, both in terms of how to properly tokenize Chinese, Japanese, and Korean jobs, as well as dealing with this accent and gender normalization issues.
Language detection options. HTTP content language response header. Most sites don't provide this header, may not be accurate.
We considered using the content language HTTP response header. Basically, when we crawl the site, we could just ask the site, just tell me what language this is. Unfortunately, most sites are not setting this header. And we also came across cases where they would set it, but it wouldn't be accurate. So we can't trust that.
Language detection. ICU4J, charset detector, works well for language with single byte encoded characters. Detect that language as one of Danish, Dutch, English, French, German, Italian, Portuguese, Swedish.
For a brief period of time, we used an open source library from IBM called ICU4J. It does some language detection. It works really well for languages whose characters fit within a single byte. So it works well for some of the languages that I've listed on this slide. It works okay for English, French, German, Italian, and some others. It does not work at all for Chinese, Japanese, Korean, Russian, and other languages.
Naive Bayesian classifier. Features, words, strong independence assumption, class label, language.
At the time, there weren't any viable open source alternatives to doing language detection, so we decided to solve this problem ourselves. We built a naive Bayesian classifier for language, and we used the words in the job description as our features. Naive Bayesian classifiers work really well when there's a strong independence assumption among the features. Here, the features are words in the job description. The probability of a word belonging to a particular language doesn't really affect the probability of a different word belonging to that language. So this seemed like a reasonable assumption to make. Also, naive Bayesian classifiers are easier to implement than more complicated machine learning algorithms. So we decided to do this. We gathered hand-labeled training data. We just use our own jobs as the training data for each language. For each language, we then calculate the probability of a word belonging to that language from our training data. For example, experience is a really common word seen in job descriptions, so the probability of experience being in English is really high.
Text equals 0.85.
And in order to actually classify the language of the job, we take the probability for each language, we take the probability of all the words in the job description belonging to that language and multiply them together. and that's treated as like the score for the job, and then we return the language with the highest score.
A chart labeled TIE with min in the top left corner and max in the bottom left corner. Two thick orange blocks appear in the middle of the chart.
Our language detector also takes advantage of Unicode blocks whenever possible. If you're not familiar with Unicode blocks, they're just named sequences of Unicode points as indicated by the Unicode consortium. So imagine that this is just the space of all Unicode characters from min to max. Then the Thai characters would be somewhere in this sequence.
The orange blocks become gray. Two more sets of orange blocks appear closer to the min and max.
Greek would be somewhere up here and down there.
Text, using Unicode blocks, 100% accurate, used in Thai, Greek, Korean, Hebrew.
So we're able to use this technique to get 100% accuracy in some languages. The way that works is that if every character in that job description falls within a particular Unicode block, say Thai, then we can say with 100% certainty that it's a Thai job. So we use this method whenever possible.
Cjk language detection. Strongly weight Hiragana and Karakana, some characters Kanji common between Chinese and Japanese. The result of a probability statement equals 0.000001.
For Chinese and Japanese language detection, we had a little bit of a chicken and egg problem. I said that we were using words in the job description, right? But we don't really have words yet because we don't know how to tokenize Chinese, Japanese, and Korean. So for those two languages, we use characters, not words. Hiragana and Karakana only occur in Japanese job descriptions, so we strongly weigh that for Japanese. Even though there are some characters, basically kanji, that's shared between Chinese and Japanese, with good training data, our detector is able to find characters that are highly likely to occur in Japanese job descriptions, but less likely to occur in Chinese.
Language results.
We validated our results by doing cross-validation. We used the same hand-labeled testing data. We found that our language detector is 99% accurate for text that's greater than 30 characters. The average job description is 200 characters, so this was plenty for our needs. Our language detector is also fast. It can detect languages at 0.6 milliseconds per job or 1,500 jobs in a second. That's pretty efficient.
Other language detectors. Google, https://code.google.com/p/cld2/.
Google did recently open source a language detector. I think it was 2013. It's called CLD2. It's written in C, and they also follow a similar approach. It's a naive Bayesian classifier. They take advantage of Unicode blocks. The big difference is that they trained using Wikipedia articles, and it detects more than 50 languages. So that's certainly an option out there for anybody that wants to use it. Now that we had language detection working, we had to come back and revisit how to actually properly tokenize Chinese, Japanese, and Korean text. This was really not an area of expertise at Indeed, so we went and researched some open source alternatives.
Cjk Tokenizers.
We found that open source text segmenters for Chinese, Japanese, and Korean text were primarily divided into two categories. They were either dictionary based or they used a statistical model and a dictionary. Dictionary based tokenizers work by taking an input list of words or a dictionary of words in that language. They simply scan the input sentence and they return all possible tokenizations. However, we found that context really matters in languages like Chinese, Japanese, and Korean. And I'm going to explain this with a Chinese example.
9 Chinese characters.
This is a sentence in Chinese. Using a dictionary tokenizer, one way to tokenize it would be Beijing, college students, come to apply for jobs.
The English text appears beneath the corresponding characters.
Using the same dictionary, it's also possible to tokenize it as Peking University, before death, come to apply for jobs. Now, everybody's laughing now. You didn't even have to learn Chinese to realize that the first option is more correct, right? Like even from looking at the translation, you were able to tell that the first way to tokenize is probably the right way. Why would anybody make a job title that says, hey, before you die, come and apply for jobs?
Preetha smiles.
And that's exactly where a statistical model helps in this problem.
The characters that correspond with the phrase before death highlight in orange.
We found that CJK text segmenters that use statistical models typically use a hidden Markov model. A hidden Markov model represents states with transition probabilities between them. And then given an output sequence, it tells you the likely sequence of states that generated that output sequence. For the problem of text segmentation, hidden Markov models states are basically words, like words in Chinese or words in Japanese. And the output sequence is the text that you're trying to tokenize.
Two arrows point from a box with the Chinese characters and English text for Peking University to boxes with the characters and text for China and before death. The arrow that connects Peking University to China is thicker than the arrow that connects Peking University to the phrase before death.
So with good training data in Chinese, and by training data I mean like somebody's gone and marked word boundaries in Chinese text. Using that training data, it's able to learn that the likelihood of seeing China after Peking University is really high. The likelihood of seeing before death after Peking University is really low.
A string of Chinese characters. A thick arrow connects boxes labeled Beijing and college student in Chinese and English. A thin arrow connects boxes labeled Peking University and before death in Chinese and English.
So then, when it's trying to decide between the two different ways to tokenize this string, it's able to pick the first option, which is Beijing college student, rather than Peking University before death.
A green checkmark appears next to the first option. A red arrow appears next to the second option.
Because the likelihood of that sequence, that is Beijing college student, generating that text is higher. The probability of that sequence is higher than Peking University before death.
Text Cjk Tokenizers.
These are the list of tokenizers that we ultimately ended up with for each language. They're all open source. They use hidden Markov models that are trained on each particular language. For Chinese, we use IMDict. For Japanese, we use Sen. And for Korean, we use Lucene Korean. There should be links on the slide. And all of these tokenizers work with the version of Lucene that we currently use in our inverted index.
Chinese tokenization. http://nlp.stanford.edu/projects/chinese-nlp.shtml.
I also want to mention that this is still an active and open area of research. There's an entire subgroup within the Stanford NLP lab that just works on Chinese text segmentation. And they publish a lot of papers, so you can go read that up if this is an area of interest to you.
Indeed, search results in Chinese, Japanese, and Korean.
Using these tokenizers, we were able to make search results look good in China, Japan, and Korea. However, we still had significant recall challenges. We found that languages had different rules around gender and plurals and collation. Since we were already detecting the language of the job, we realized that we could take words in each language and apply language-specific rules to transform it into a canonical form. We call this stemming.
Text, what is stemming?
So the definition of stemming is that taking multiple variations of a root and of a word and transforming it into a single root. You can think of stemming as essentially the process of creating equivalence classes. So here, driver and drivers is an equivalence class that stems to driver. Secrétaire in French spelled with and without the accented E. Vendeur and vendeuse, which is male and female form of salesperson, which stems to vendeur. And when I say equivalence classes here, I mean that if anybody searches for driver, we want to show jobs containing driver and drivers. Same thing with the other examples. If anybody searches for vendeur, we want to show jobs containing vendeur and vendeuse. Why does stemming matter to us? We really want to return all possible relevant jobs given the job seeker's query, not just exact matches. So this is an important problem that we had to solve.
Stemming Lucene analyzers. Do stemming before adding to inverted index.
Since we were already using Lucene, we went and looked at what stemmers were available within the Lucene project. And there are some examples listed here like English minimal stemmer and Porter's stemmer filter and Snowball analyzer. They all apply different stemming algorithms, but the one thing that's common between all of them is that they perform stemming before adding the term to an inverted index. Let me explain what that means with the specific example.
An inverted index for French jobs with columns labeled token, job A, and job B.
Let's say we had two jobs in French. Job A is directories d documentaire, and job B is director et production. So the first one is documentary director, the second one is production director. Then using a Lucene stemming analyzer, that first job, when it's processing the keyword directories, it would apply a French stemming rule and turn it into the root form of director. So the inverted index shows that both job A and job B have the term or token director.
Text search with stemming tokenizers.
Then at search time, you would use the same analyzer on the query as well. So when somebody types in directories, you would apply a French stemming analyzer, which would turn the word directories into director. So even though the job seeker searched for directories, internally it does a search for director, and it's able to return both jobs. This seems like a reasonable approach, but it had a pretty major drawback that we wanted to fix.
Modifying stem rules require full index rebuild. If roots have changed, need to reprocess all jobs.
The drawback is that if stemming rules change, then we need to do a full index rebuild. What does that mean exactly? So if a stemming rule changes, that means that the root form of the word could have changed as well. If the root changes, then we have to redo and reprocess all our jobs.
Pritha returns to the French inverted index.
So going back to that same inverted index again, it had a different word, documentaire, plural. And let's say we wanted to do plural stemming, so we wanted to remove the S at the end. This means we would have to find all jobs that contain that keyword and run them through the French stemmer and add them back to the inverted index the correct way, which would be with documentaire. This takes hours on our index, which has millions of jobs. And we really pride ourselves on being able to get jobs to job seekers as quickly as possible. If you went and did a job search on Indeed and selected sort by date, most likely you'll see that the most recent job is anywhere from 7 to 10 minutes old. So taking hours just to fix stemming was not acceptable to us. You could also argue the same thing with rollbacks. So say we made a mistake, we introduced a code bug in our stemmers, and then we pushed it out to production, and we realized it a couple of days later. We have to, again, pause everything, delay getting jobs to job seekers until we go back and reprocess all those jobs and add them back to the inverted index. So this was not a viable option for us.
Text drawbacks.
There's another subtle drawback with this approach, which is that there's a loss of precise information. So by convention in search engines, if somebody puts quotes around the search term, then it should return only exact matches. So directory search with quotes around it should return exact matches. But our inverted index doesn't even have the term directories because we turned it into director. So we're not able to serve this search. The main insight we had was that we needed to decouple stemming from indexing. And our solution for this is called term expansion maps. Term expansion maps are the core data structure used to implement stemming at Indeed. It's basically a map from a string to a list of string, where the key is the root and the values are all the tokens that stem to that root. So here are some examples. Driver is the root, driver and drivers are the values or expansions. Wander is the root, and wander and wandus are the expansions. We created a stemmer interface in Java. It had a single method, stem. Its job was to take a token, perform stemming, and return results. It had many implementations, essentially one per language. Like English stemmer would deal with English stemming rules, French stemmer would deal with French stemming rules, and so on. We had to figure out how to actually build these term expansion maps. So for each language and for each term in that language, we can basically invoke the language-specific stemmer on the term and get the root, and then we can update the term expansion map with the data for that root. So here's just 4 lines of pseudocode explaining how to do that.
Line 1, for each language. Line 2, for each term in language. Line 3, root equals stemmer.stem open parentheses term close parentheses. Line 4, term map open square bracket root close square bracket dot append open parentheses term close parentheses.
Lucene provides a low-level term enumeration API that's very efficient. So doing this process takes only about 1.5 minutes on an index with millions of jobs. and millions of tokens and 18 languages.
Using term expansion map.
So I talked about how we actually build term expansion maps, but we still need to figure out how to use it at search time to achieve the same results as before. That is, a search for directories should return jobs containing director and directories.
Pritha returns to the French inverted index.
So here's our inverted index with the old method with the Lucid method where, the inverted index has just one token director and it says both job A and job B had it. When we're using term expansion maps, we go back to indexing the term just the way we found it. So it shows that job A had directories and job B had director. Now somebody searches for directories, the first thing we do is run it through the French stemmer so we can turn directories into director.
In a diagram, arrows connect each step of the process Pritha explains.
Then we pass that through a query rewriting module which loads the term expansion maps that we generated. The term expansion map would have an entry for director, which is all the values that stem to director. So an entry for director would have director and directories. So then the query rewriter uses that information to produce a Boolean query, director or directories.
Pritha returns to the French inverted index.
Here's our inverted index again. If you did a Boolean query for director or directories, you will get jobs A and jobs B, which is what exactly we wanted.
Text, benefits.
So the main benefit of this method is that modifying stem rules don't require expensive index rebuilds. It only takes minutes to do this for an index with millions of jobs. So we really had the flexibility to iteratively implement stemming use cases as we came across them in the early languages that we did, like French, German, and Spanish, where we weren't quite sure exactly all the stemming rules that we needed. So we were able to iteratively add them to the code as we came across them.
Precise information.
We have our precise information back. When somebody does a quoted search for directories, we can just choose not to apply stemming rules, look up in our inverted index and return all jobs that contain that term. However, we were still doing code deploys to change rules and add additional languages.
A team of people wears "I help people get jobs" t-shirts. Text, 49 team members, 26 nationalities, 18 languages.
If you came to our last tech talk, we talked about our international team. So we have an entire team here. We call them, and some of them are country managers, and they represent 26 nationalities and they speak 18 different languages. They're really the product owners. So they're responsible for their country and their language. We wanted to give them the power to be able to, for them to own stemming and not have to coordinate with the developer if they wanted to make changes to stemming.
Text, scale stemming.
So basically, Indeed wanted to keep scaling and continuing its international expansion, and we really needed stemming to scale without expensive code deploys and coordination between developers and our country managers. We came up with some goals for what this new stemming system would do. The first and most important goal is efficiency. Speed and efficiency is critical to everything that we do here at Indeed. We knew that our term expansion maps would have potentially millions of terms in dozens of languages, so we wanted a very efficient way to store them. Search should be as fast as possible. We don't want to slow down search for implementing stemming. We needed it to be generic.
Identify patterns common to all languages.
We looked at the code that we'd already written for English and Spanish and French, and we saw that we were doing sort of the same thing everywhere. For example, in English, we would take IES at the end of the word and replace it with Y to do plural stemming. In French, we would take SE at the end of the word and replace it with R to do gender neutralization. So both of this seem like similar patterns, so we should be able to exploit that. It should be comprehensive. So we have a lot of different use cases. We had to support plurals and synonyms and abbreviations and accent collation and gender suffixes. So we wanted to build a system that was powerful enough to support all of these use cases. It should be scalable, like I already mentioned. We don't want to have to do a code deploy every time we have to add a new language or modify existing stemming rules. The system that we built to address these goals is called rule-driven stemming. The basic concept is there's one generic stemmer that stems all languages, just like one search, all jobs.
What is a stemming rule?
So in order to build a generic stemmer, we needed to take a step back and really define what exactly is a stemming rule and how to use it. So to us, a stem rule is something that transforms tokens into their root form.
Rule attributes.
By definition, since it's a transformation, it has to have from and to parts. We call this origin and replacement respectively. Rules have a type associated with them. The type defines exactly how the text transformation happens. We have 3 major rule types, and I'll go over them one by one. The first rule type is exact. So the way exact rules work is that they change the origin to the replacement when there's an exact match. We use exact rule types to implement abbreviation expansion as well as synonyms. Here are some examples of some exact rules we have in different languages. So in English, we have an exact rule that causes SR to expand to senior. This means that if you look for senior developer jobs, you're also going to get SR developer jobs. A similar one to do synonyms of attorney and lawyer. There's an Italian rule that's an exact rule that does call to domestica. That's actually domestic worker in Italian. And then there's the Dutch rule for teachers, 2 synonyms of teacher. The next rule type that we have is substring. Substring rules work by changing all occurrences of the origin to the replacement. We primarily use substring rules for accent collation. So here are some substring rules and different use cases and different languages. There's one in English with E with an accent, and that makes sure that resume spelled with accented E also matches, stems into resume without the accented E. Similarly for cafe. The German one is A with an umlaut, so that's used for Verkäufer. I don't really know what that means, I forgot, but you can look it up. The French one is O with a caret on top, and that's also doing a different kind of accent normalization or accent collation for hostess in French. The next rule type that we have is suffix rules. Suffix rules work by changing the origin to the replacement if it matches at the end of the token. We use suffix rules to implement plural as well as gender plurals and gender normalization. Here's a suffix rule in English. A couple of suffix rules in English: IES to Y, which is used to stem families to family or policies to policy, and then S to empty string for nurses and so on. Here are some suffix rules in French. They're doing gender normalization, so EUSC to ER for servers to server and gardien to gardien.
Rules are ordered.
Rules, our system supports rules having order, and this is important, and I'll explain why with an example. Let's say we wanted to stem families, and we had the 2 English plural rules, plural stemming rules that I had mentioned earlier, S to empty string and IES to Y. If we applied S to empty string first, then families would become family, which is incorrect.
A red X.
The correct way to have done this would have been to apply IES to Y first, and then the S to empty string would no longer match, and we would get the right results. So our system needed to support having a predefined order for rules. We can also mark rules as terminal rules. A terminal rule means no additional rules can apply after them. This is used in case of languages where you have more than one plural rule, plural stemming rule. There's no need for the same word to have more than one plural stemming rule applied to the same token, so we can use that. It's also used in case of synonyms, where we've already decided that this is the final form of the word, and we don't really want to make any further changes. Then we can mark that rule as terminal. Another thing that we had to do was prevent overstemming. So for example, the suffix rule S to empty string can cause this to become THI, which is unintentional, and we don't want that. So we get around that by creating a special rule called a min-length rule. A min-length rule is always terminal, and it's usually set anywhere from 3 to 5 depending on the language. We just use this to make sure that we're not overstemming and ending up with really short tokens that don't that start to affect precision.
Text, Babelfish, stem rule editor.
We built a web app in order to be able to edit and publish these rules. our country managers, who are the language experts and the product owners for each country, manage their STEM rules using this web app. It's called Babelfish. It's a nod to Douglas Adams. I think it's a fish that like sits in your ear and translates things to you. So it was named after that. The rules are interpreted, the rules that you create in Babelfish and say and publish are interpreted by a generic code stemmer, and we use this system for 27 different languages today. Here's a screenshot from some rules in Babelfish from German.
In Babelfish, orange boxes around rules 73, 74, and 81.
It's showing you rules from 73 to 81. There's actually over 100 stemming rules just in German. There's some suffix rules, and then there are some exact rules.
An orange box around rules 75 to 79.
All of those exact rules are basically synonyms for temporary help in German. And then there's a substring rule here.
An orange box around rule 80. Text, ability to audit rules.
Babelfish also lets you audit rules. This is super useful when you're debugging or really trying to understand what stemming rules are applied to a particular token. So here we have a couple of examples. So directrices, we started out with directrices and we ran an audit. The first thing it did was apply the suffix rule s to empty string to do plural stemming, so it turned it into directories. Then it applied a different suffix rule to do gender normalization, so it matched the TRISE to TEUR. So we started with directrices and we ended up with director. The second example is only applying one rule, but it's a substring rule to get rid of the accented E.
A flowchart.
This is the architecture of the entire system. So we have our country managers who are using Babelfish, the stem rule editor, to edit and publish these stem rules.
An arrow connects country managers and stem rule editor. An arrow connects jobs to index builder.
Then these stemming rules. Then our index builder loads these stem rules and uses the index and the stem rules in combination to produce a term expansion map.
An arrow connects stem rule editor to index builder. An arrow connects index builder to term expansion map.
The term expansion map has things like, root to expansion, so sale to sale and sales and so on.
An arrow connects term expansion map to search service.
Then this term expansion map, in turn, is loaded by our search service and used to serve job seekers' queries.
An arrow labeled query connects job seekers to search service. An arrow labeled results connects search service to job seekers. Text, term expansion map storage.
Like I mentioned earlier, we needed to figure out how to store these term expansion maps efficiently, because there are some indexes that have dozens of languages and millions of terms. So we came up with a custom serialization format for this. We store string arrays as UTF-8 byte arrays with integer offsets to indicate where each string begins and ends. And we additionally do front encoding for more compression. Front encoding works particularly well when your data is sorted. So since term expansion maps are sorted, it works out pretty well. Doing this, our term expansion maps are 2 times smaller than they would have been had we used native Java serialization. Our stemming system is comprehensive. It can handle gender and accents and plurals and synonyms. It's scalable. We went from 4 Java classes for French, German, Italian, and Spanish to 27 different languages supported using this method.
Stemming rules.
We were also able to reuse all of this work when we launched our resume search product, both the language detection and the stemming work.
Efficient.
All of this is done very efficiently. The term expansion map in Europe, for example, has 2 million terms in 18 languages, and that's just 60 megabytes on disk. Building these term expansion maps takes about 1.5 minutes. We build them either once a day or whenever stem rules change. So that's an acceptable time for us. Doing the Boolean query for making stemming works adds about 5 milliseconds to our median search time. So our median search time is 35 milliseconds, which is also pretty cool. Most importantly, stemming really helps job seekers. Searches that return no results reduced by 60% after we had stemming. Also, we got 3 to 5% more clicks because of stemming. Everything that I just talked about went into details of what we did to help job seekers around the world at Indeed. Now over to Dan, who's going to talk about what we did to help employers around the world at Indeed.
Dan returns. Text, multi-currency sponsored jobs.
As Preetha mentioned, I'm going to talk a little bit about some of the work that we've done to internationalize our products for employers.
Dan returns to the Indeed job search for software jobs in Austin, Texas.
Again, here's an example screenshot of a search results page.
An orange box around 2 sponsored software engineer jobs.
If you look at the top of the page, you'll see that these 2 results are what we call sponsored jobs. And here, an employer has decided they want to sponsor their jobs in our search results to drive more traffic and visibility for these jobs.
Text, sponsored jobs at Indeed.
The way that we determine this is we use a real-time auction to determine which jobs will get these sponsored impressions at the top of the page. Our auction system uses the expected value of the impression to determine which jobs to show. And what I mean by this is that we don't have an auction where the highest bidder wins the impression. We use a combination of the employer's bid as well as the expected click-through rate. So quite simply, the formula for expected value is bid times the expected click-through rate.
The word bid highlights in orange.
This formula works well because the bid represents the value of the job seeker's traffic to employers.
The phrase expected click-through rate highlights in orange.
The expected click-through rate represents how relevant that job is to the job seeker's query. We could spend a whole nother tech talk talking about how we do a good job of predicting that expected click-through rate. We did talk a little bit about it in the tech talk back in February, which was called Scaling Decision Trees. And if you go to the Indeed Engineering Talks page, you can find the full video there. But for now, let's just assume that we can do a good job of predicting the click-through rate of the job seeker.
A table with 2 columns labeled job and bid.
So let's walk through an example. Suppose that a job seeker comes to Indeed and does a job search, and there are 3 sponsored jobs that are relevant to them. Jobs A and B and C. And the employers for those jobs have said that they're willing to pay $3 per click, $2 per click, and $1 per click for traffic to those jobs.
A third column, labeled ECTR, job A, B, and C have expected click-through rates of 5%, 10%, and 8%, respectively. A fourth column, labeled value, appears.
We compute the expected click-through rate for each job with respect to the query that the job seeker's done, and we multiply those 2 together to produce the value. So here, job A has an expected value of 15 cents, job B is 20 cents, and job C is 8 cents.
A fifth column, labeled rank, appears.
We then rank these results using the value, and we find that job B will be in the first position in the sponsored results, and job A will be in the second position. If we look more closely at job A and job B, we find that job B could have won the first position with a lower bid. They didn't need to bid as high as $2. And so we don't want to charge them $2 for this click. We only want to charge them as much as they would have needed to pay to be in the first position.
Text, only charge what's needed to win.
It turns out that in this case, they only needed to pay $1.50, or to bid $1.50, which would have given them the same value as the job and the position behind them. And of course, we want to make sure they're paying a little bit more than that. So in reality, we'll charge them $1.51.
Orange boxes around 15 cents, the expected value of job A, and 10%, the expected click-through rate of job B.
And turns out the way that you can mathematically calculate this is you take the expected value of the job and the position behind, and you multiply that by the expected click-through rate of the job that you're looking at. So here we take 15 cents and we divide by 10%, and that gives us $1.50.
Text, sponsored jobs at Indeed.
This model is very common in online advertising networks, and it's usually referred to as a generalized second price auction. We use it here at Indeed because it's fair for employers. Employers, when they're paying for traffic, they won't pay their bid. They'll only pay as much as they needed to pay to get the click. Additionally, This model ensures that the sponsored results that we're showing to job seekers in search results, that they're relevant to job seekers and that they're useful for job seekers.
Employers set their bid and budget.
So here's how this works. We already have all of the employers' jobs on our site. And so employers just need to come to Indeed and tell us which jobs they're interested in sponsoring. And they let us know what their bid and budget is for the job or groups of jobs.
A code string. Line 1, employer underscore ID int open parentheses 10 close parentheses unsigned comma. Line 2, bid decimal open parentheses 10 comma 2 close parentheses unsigned comma. Line 3, daily underscore budget decimal open parentheses 10 comma 2 close parentheses unsigned comma.
Originally, we were focused on the US market. And so when we stored this information in our database, we used a representation for currency values, which was really focused on US currency. So you can see here, the bid and daily budget use a fixed point notation because in US currency, we have 1/100th of a dollar as the smallest unit that we charge for. We then have a builder process that takes all of the sponsorship information and builds read-optimized data structures that allow our auction system to execute extremely performantly.
Dan returns to the Indeed job search for software jobs in Austin, Texas. An orange box highlights 2 sponsored software engineer jobs.
On each search results page, we execute an auction among the jobs that are sponsored and relevant to the query, and we determine which jobs should get the impressions.
Text, sponsored jobs at Indeed. When job seeker clicks on sponsored result, log information from the auction. A log includes employer ID, job ID, bid, and cost.
When a job seeker clicks on one of those jobs, we redirect them to the site where they can apply to the job, but we also log the results of the auction. Later on, we'll process these logs to update the budgets associated with each job and to charge and invoice employers. We also apply business rules during click processing, such as fraud detection and duplicate click detection.
Text, SJ outside the U.S. Non-U.S. employers wanted their jobs in sponsored results.
And so this worked really well. It allowed employers to sponsor their jobs on Indeed, and as we grew internationally, international employers also wanted to sponsor their jobs within our search results. The problem was they didn't have US dollars. They had yen, or Canadian dollars, or euros, or the currency of wherever they were located. The solution we had for them was to use credit cards. And so they would come, they would enter their credit card information, and then at the end of the month, we would charge them for their traffic in US dollars. The credit card company would convert that US dollar charge to their preferred currency.
No changes needed.
This worked well because it allowed international employers to get started with Indeed and to be sponsoring their jobs and to engage with job seekers. It didn't require any product changes or changes to our invoicing systems. There were some downsides to it, though. First of all, it was a terrible user experience for employers. Instead of, when an employer wanted to say how much they wanted to spend each day on a job or how much they were willing to spend for traffic, instead of providing those in their preferred currency, they would have to convert to US dollars, and so they'd have to look up the current exchange rates and things like that. Additionally, in the reporting and analytics that we provide them, the results that they'd see would be in dollars, and they'd have to convert that back to their preferred currency. Second, it meant that employers were getting disadvantaged exchange rates. So typically when the credit card companies are converting the charges to the employer's preferred currency, they'll either give a non-preferred exchange rate or they'll charge a transaction fee for the foreign currency transaction. Lastly, this setup was forcing our employers to bear the risk of currency fluctuations.
Credit cards, currency risk.
And what I mean by that is, let's say that on January 1st of this year, a Canadian advertiser came to Indeed and wanted to spend 100 Canadian dollars every day sponsoring their jobs. If we only accepted US dollars, they'd have to convert 100 Canadian dollars to US dollars. The exchange rate on January 1st was 0.9351 US dollars for each Canadian dollar, meaning that they'd set their daily budget to $93.51 in US dollars, which would be equivalent to 100 Canadian. Over the course of the month, though, that exchange rate fluctuates. And by the end of January, the exchange rate is 0.8970 US dollars for each Canadian dollar. And so that $93.51 daily budget that they set is no longer equal to 100 Canadian dollars. It's now equal to 104.25 Canadian dollars. This is a difference of 4.25%. And so this is just the variance over 1 month. Over longer time periods, that could be even more. And so we decided that we needed to implement a true multi-currency sponsored jobs auction. We had several goals when making this change. First and foremost, we wanted each employer to be able to set bids and budgets using their own preferred currency. So here on the screen, we have the 6 currencies that we targeted initially: Canadian dollars, Australian dollars, Japanese yen, the euro, British pounds, and Swiss francs. And on the right-hand side, you can see the 3-letter currency codes that we often use as an abbreviation.
CAD, AUD, JPY, EUR, GBP, CHF.
Second, we wanted to make sure that we had a single auction for all employers, no matter what currency they were using. A good example of this is multinational employers who have jobs around the world. For example, a US employer has jobs in Germany, or a French employer has jobs in Canada. They want to be able to sponsor jobs in both of those countries using the same currency system. And so this meant that having the auction in the UK use British pounds and the auction in Germany use euros would not be a good solution, because again, that would require employers to be constantly using different currencies that they're not familiar with. We also wanted to have fair exchange rates for employers. Indeed is not a financial services company. We make money by helping employers connect with job seekers. And so we don't want to make money on transaction fees or higher exchange rates. Lastly, we wanted to have transparent and repeatable calculations. And the real driver for this is that we wanted to use integer arithmetic everywhere that we were doing calculations and computations within the auction. And this is important because that meant we could re-implement parts of the advertising system in different programming languages, different technologies, different architectures. And we could have high confidence that we were going to get the same computational results with all these important calculations. Our solution was to create a new pseudo-currency that we call Millicents. And this is used just within the auction. And a millicent is 1/1000th of a cent. So the exchange rate between millicents and US dollars is fixed. 1 penny is 1,000 millicents, and $1 is 100,000 millicents. Additionally, the exchange rate between millicents and other currencies will float and fluctuate over time. As of June 1st, 1 euro was equivalent to 136,170 millicents, and 100 yen was equivalent to 98,350 millicents. But again, those change over time, and we update them every day. The reason we chose millicents was because it gave us enough granularity to differentiate between very similar values in different currencies. And so as an example, we have a few different currency values here on the screen. $1 USD, 60 pence in British pounds, 73 euro cents, and 102 yen. And it turns out all of these are pretty much equal to each other. They're all about $1.
Which is larger?
In the auction, though, we need to rank these because they might be different bids from advertisers using different currencies. So we need to know which one's larger.
Converting to USD doesn't help. Arrows connect each currency value to $1.
If we were just converting them all to US dollars, and again, using integer arithmetic with cents, we would find that we can't tell the difference between them. They all look the same. If instead we use millicents, though, we can tell the difference between them. And so we'd find that 60 pence is the largest of these, and 73 euro cents is the smallest.
Text $1 USD 100,000 millicents 0.60 GBP 100,450 millicents 0.73 EUR 99 519 millicents 102 JPY 100,317 millicents.
We have the convention that when we're representing the value associated with a single sponsored job click, we can use a 32-bit signed value to represent the cost in millicents.
$21,474 USD equivalent.
And when we're aggregating costs across multiple clicks, we use 64-bit values. This allows us to represent values for a single click up to 21,000 US dollars, and across multiple clicks up to 9.2 trillion. So clearly this gives us enough range that we can express all the values we need to.
Local currency values. Values in specific currency are represented with currency code and an integer. Integer represents minor unit, depends on the currency type.
We also needed to change how we represent local currency values. If you remember, earlier in the database, we were storing bids and budgets using a fixed point notation where we always had 2 decimal places. That makes sense for dollars and a few other currencies, but there's some currencies, such as yen, where that's not appropriate. And so what we do is we store local currency values but as an integer and a currency code. And so we have a different minor unit for each currency code, and this minor unit represents the smallest value that we can represent there. And so the interpretation of that integer depends on the currency code we're talking about. In US dollars, the integer 543 would be $5.43. In euros, 543 represents €5.43. In yen, on the other hand, because the scale is different, 543 represents 543 yen. It's important that for each currency, this minor unit is about equivalent to 1 US penny. There's 2 reasons for this. One is, again, because we want to use all integer arithmetic, the exchange rates are internally represented using integers. And so to make sure that we could have the same amount of granularity on our representing exchange rates, it's important that the minor unit for each of these currencies is about equivalent to a penny. This is also important because we want to make sure that our auction is fair to all of our employers. If there was one employer who was using a currency where their minor unit was much smaller, they'd have an advantage in the auction competition and might be able to game our results. So we wanted to avoid that.
32-bit signed values, $21 million USD and others, 2.1 billion JPY. 64-bit signed values, 90 quadrillion USD and others, 9 quintillion JPY.
Again, we have the same convention with local currency values that we do for millicent values. For a single click, we use a 32-bit signed integer to represent the costs associated with it. And when we're aggregating values across multiple clicks, we use 64-bit signed values. Again, we have the ability to represent every possible value we could need to. And so now that we determined how the multi-currency auction was going to work and be structured, it was time to make all those changes. So we changed all of our bid and budget representations to use currency and integer instead of the fixed point notation. We created a process to retrieve and record the exchange rates every day. We actually work with multiple currency exchange rate providers just in case one of them has a problem. The auction builder process that created the highly performant data structures, it is also responsible now for doing the conversion from each employer's preferred currency to the common millicent currency. It's also going to save the exchange rate that was used to do that conversion. The auction now executes in millicents instead of specific to US dollars. And we're going to record all the auction results both in millicents and local currencies.
Add multi-currency date to click logs. On the left, an old click log includes employer ID, job ID, bid, and cost. On the right, a new click log includes employer ID, job ID, currency, exchange rate, bid in currency, bid millicents, cost millicents.
And so in the click logs, instead of just logging the bid and the cost, we're now additionally going to log the currency and the exchange rate of the employer and the conversion to millicents. We're going to log the employer's bid, both in their local currency and in millicents. And the results of the auction, that cost will be logged in millicents. During click processing, we're going to convert that millicent cost back to the employer's local currency, and we're going to use that exchange rate that we saved earlier. It's important to use the same exchange rate so that the final cost that we're going to be charging to employers will be less than their bid. One problem we realized we were going to need to rethink was some of the internal reporting that we do. So sometimes we ask ourselves, how much revenue did we make today? And let's just say that on a given day, the answer was $1,000. In a multi-currency world, that doesn't make sense anymore. We didn't make $1,000. We made some US dollars, some euros, and some yen. And so here we made $548, 273 euros, and 8,253 yen. All of these together are about equivalent to $1,000. But they're not exactly the same. Internally, we might say that we made 100 million millicents. Which sounds like a lot, but it's really just $1,000. If we're aggregating values this way internally, we could just, on the front end, display this as equivalent to 1,000 US dollars.
Revenue reporting.
The problem, though, is if we aggregate the millicent cost from the auction, there's going to be accumulated errors. As an example, suppose that we have a click resulting from the auction, and the cost of that click is 53,826 millicents. Now, this click was for an employer that's using euros. So we need to convert that back to euros, and we get 0.39483 euros. We can't charge an employer that amount of euros. We need to charge them in increments of 1/100th of a euro. So we're just going to charge them 39 euro cents. That 39 euro cents, though, isn't equivalent to the original millicent cost. It's equivalent to 53,168 millicents. And that's a difference of 1.2%. And so what we do is we use that actual millicent cost when we're aggregating costs for internal reporting, because it's a more accurate representation of the revenue that Indeed is going to recognize from this click. And over a large number of clicks, over millions of clicks, that difference could add up, and it would also be unpredictable.
A line graph titled Active Non-US Employers. On the x-axis, January 2012, 2013, and 2014. 3 lines for Canada, Great Britain, and Japan trend upward.
All of these changes to support multiple currencies have really helped us be successful outside of the US with non-US employers. So you can see here, over the last 1.5 years since we've introduced the multi-currency auction, our ability to work with employers in Great Britain, Japan, and Canada has continued to increase.
A graph titled 30% of sponsored clicks non-USD, on the y-axis, 0 to 30% in increments of 10. On the x-axis, 2013, April, July, October, 2014, April. A red line starts at 0 and trends upward to 30% between 2013 and 2014, with minor dips and rises throughout. The portion of the graph below the line is pink. The portion above the line is purple.
The popularity of non-US currencies can also be seen here. This is a graph that shows what % of the sponsored job clicks on Indeed are in non-US currencies, and we're now at about 30%.
A world map labeled 2004. The United States is shaded orange.
So when Indeed started back in 2004, we were focused on US job seekers and creating the best job search experience for job seekers in the US. And now 10 years later, we're focused on job seekers all around the world.
A world map labeled 2014. Many countries are shaded orange.
Last month and tonight, we've talked about a lot of the challenges and investment that we've made to make sure that our products and our job search is the best in the world. And as you can see, that's paid off. We're now #1 in many of the markets we work in, and we're continuing to invest all around the world to improve Indeed for our job seekers and employers. Thanks.
Attendees applaud from their seats. Indeed logo. Text 1 search. All jobs.